Welcome to this lecture series in linear algebra. We will continue our discussion from last time, and in this lecture we'll prove something very interesting and define a new concept before that. Let us recall what we need to follow this lecture. So we have seen earlier when we were proving the primary decomposition theorem, the following fact, which says that if suppose we have an endomorphism on a vector space V and we have two relatively prime polynomials over the base field, f is the base field of V, then the kernel of the product of these two things is the direct sum of the individual kernels. Alright, and this was the main lemma behind the primary decomposition theorem. We will need the primary decomposition theorem also. Let me not recall the statement of this because we have done this so many times. Alright. Of course, we will need the definition of eigenpolynomials, and we will need the fact that we proved that the eigenpolynomials of any endomorphism are precisely the monic irreducible factors of the minimal polynomial of the endomorphism. Alright. Finally, we defined the algebraic multiplicity of an eigenpolynomial corresponding to, or eigenpolynomial px of an endomorphism T in some way, but it was essentially this equation. So either you define it this way or you define it the way we defined it, it's not much different. So anyway, we just need to know that the algebraic multiplicity of an eigenpolynomial is given by this expression. Of course, we will leverage on many other facts that we will not recall. But yeah, this lecture will be in some sense borrowing more from previous lectures than any other. Anyway, here is one problem for practice. And now let us get started. So before we get started with the lecture proper, we need to kind of prime ourselves with this fact about minimal polynomials. What does it say? Suppose we have an endomorphism and whose minimal polynomial is mx. Suppose ax is a irreducible factor of mx, and k is the largest power of this polynomial which divides mx. So ax to the power k divides mx, but ax to the power k plus 1 does not divide mx. That's what this means. Then k is at most the dimension of the vector space. Okay. So, I will not be proving this. This should be clear to you by now, these things. Basically, the point is this. Let's say the minimal polynomial is ax to the power k times something, let's say sx, where of course sx is relatively prime with ax, because k is the largest power of ax that divides mx. So what we get is that kernel of mt, which is nothing but v, is the direct sum of these two things. And if k were larger than, so before I even say that, we just need to note that this kernel is properly contained in this kernel, is properly contained in so on, properly contained kernel at to the power k. Because if any of these containments were not proper, we would see that a lower exponent here would also serve the bill. So that is essentially the reasoning. I'm not doing it in full because this kind of thing we have already seen many times. So this particular fact, I just leave as an exercise. It is an important exercise. If you somehow this is not clear, you should spend time on it. Okay? All right. So now we start with the lecture proper. Suppose we have an endomorphism on a vector space V, and px is an eigenpolynomial of the endomorphism. Then we define the saturation exponent of the eigenpolynomial. We write this symbol, and again, this is a non-standard terminology. So let me just record that here. This is not standard. You will not find this expression in textbooks. And I don't know if there is some other name by which this is referred to. I don't know. Perhaps there is. Yeah, so the saturation exponent of this eigenpolynomial is written this way and defined as the smallest k such that the dimension of the kernel of pt to the power k is equal to the algebraic multiplicity. And let me not use k because that might get confusing. Let me use some other symbol. Let me say L. Okay. Obviously, I mean natural numbers. There's no need to write it, but let's write it. So that's the definition of the saturation exponent of this eigenpolynomial. And here is the main fact. So the saturation exponent of the eigenpolynomial px is same as the largest power of px, which divides the minimal polynomial of t. So as we recalled, since px is an eigenpolynomial, it is an irreducible factor. It is first of all an irreducible polynomial. Further, it is a factor of the minimal polynomial because eigenpolynomials are precisely the monic irreducible factors of the minimal polynomial. So this does divide the minimal polynomial of t, and we are saying the saturation exponent of px is same as the largest power of px that divides the minimal polynomial of t. Right? So it's the largest L such that this divides mx, where this is the minimal polynomial. Okay, so let us start with the proof. So let k be the largest power of px that divides mx. Where what is mx? Mx is the minimal polynomial. Okay. So then, as we, the exercise that I left you with in the beginning, we know that k is at most the dimension of the vector space V. And therefore, we can write the following. Clearly, because k is at most dimension of V, we can write the kernel of this endomorphism is at most the kernel of that. In fact, this kernel is contained in that, so we can write this. The thing on the right side is the algebraic multiplicity of the eigenpolynomial p, and here we can write a strict inequality. So why can we do this? K is by definition, k is the largest power of px dividing the minimal polynomial. If this were an equality, the only other possibility is that this is an equality, and if that were so, then the minimal polynomial would have a smaller degree, because the largest power of px, what I'm saying is just use the primary decomposition theorem. If this were an equality, you can deduce using the primary decomposition theorem that the minimal polynomial would have a smaller degree, and that would be a contradiction. So please make sure you get this point. Okay, and because of this, we know that k has to be at most the saturation exponent. Or maybe saying it the other way, that the saturation exponent has to be at least k. Saturation hasn't occurred up until the point k minus 1 because there is a strict inequality between this dimension and this number. So saturation hasn't happened up to k minus 1. And therefore the saturation exponent has to be at least k. The saturation will happen either at k or somewhere after k. Okay, so to finish the proof, all we need to do is show that we claim that this dimension is actually equal to the algebraic multiplicity. And that will show that this is actually an equality, that the saturation has happened at K. Okay, so this is now our goal. Okay. So since this is a new page, let us rewrite, or not rewrite, let's say mx is written this way. So it is equal to px to the power k, because k is the largest power of px that divides mx. So mx can be written as px to the power k times p1x to the power k1 dot dot dot, where of course these p and p1 up to pr are pairwise distinct monic irreducibles. So let me write that. Monic irreducible polynomials over the base field. That I'm not writing. Okay, so we have that, and define capital Mx as this funny polynomial. Since k and all these ki's are at most the dimension of V, we have this divides that. So again, why is this? This is what I left you with. This is the exercise that I left you with. So this obviously implies that. And therefore, let me write here, this implies MT is the zero polynomial, zero endomorphism. Therefore, V is nothing but the kernel of MT. But here is the key idea. These are your pairwise relatively prime polynomials, because Px, P1x up to Prx are pairwise relatively prime, because they are pairwise distinct monic irreducibles. So these are pairwise relatively prime, and hence these are also pairwise relatively prime. And hence, by what we recalled in the beginning, the kernel of MT is nothing but the direct sum of the kernels of the participating guys. Right? This is by the fact we recalled in the beginning, in the recap. So we have that. But at the same time, by primary decomposition theorem, we also have that V is nothing but this direct sum. Okay, so we have two different direct sum decompositions of our vector space, but this is clearly contained here, and each of these is contained there. So for every I, this is contained there. So by this equality, it follows in particular, this follows. This also is true for each I, but we don't care about the other I's. So we have this. So once we have this, we see that dimension of the kernel so we just took dimensions on both sides, and the right hand side is nothing but the algebraic multiplicity of the eigen polynomial P. Yeah. So another way to, or rather one implication one can draw from here is that this is less than equal to K, and we had already seen the reverse inequality. Basically, this proves our claim. I mean, this was our pink claim in the previous page, but anyway, that implies this, and we had already seen that, and hence this must be equal to k, and that was the statement of the proposition. So we have proven our statement, and in particular, what we have done is the following. In the course of this proof, what we have shown is the following. If we have an endomorphism on a vector space V and Px is an eigen polynomial of the endomorphism, and this is the algebraic multiplicity, then, well, this equation holds immediately by the definition of the saturation exponent. But what we have shown is that this is actually equal to that, where k is the largest power of Px that divides the minimal polynomial of T. So this is what we have shown in the previous argument. This is contained in the previous proposition, I mean. Okay, and now an important consequence of this thing is the following. Fix an endomorphism on a vector space V, and P1 up to PR be all the eigen polynomials of T. In other words, P1 up to PR are all the monic irreducible divisors of the minimal polynomial of T, because eigen polynomials are precisely the monic irreducible factors of the minimal polynomial. Alright, so then the conclusion is that the algebraic multiplicities of all the eigen polynomials sum up to the dimension of V. Very interesting. And here is the proof. The proof is primary decomposition theorem. That is the proof coupled with what we have proven in the previous slides. So say the minimal polynomial, mx is the minimal polynomial. Let me not write that. So say this is equal to p1x to the power k1 dot prx to the power kr. So by primary decomposition theorem, we have that, which implies dimension of V is this expression, but this is the algebraic multiplicity of the eigen polynomial Pi. This is what we showed in the previous slides. So we have our statement. All right. So what you can do is, for now, just think about what this says if your vector space was a sorry. If the vector space V were a complex vector space, then eigen polynomials are essentially just the same as eigenvalues, because there will be no degree 2 irreducible polynomials. So these are all degree 1 polynomials, and hence they are essentially just eigenvalues. So it says that the algebraic multiplicity of all the eigenvalues sum up to the dimension of the vector space whenever V is a complex vector space. So that's a nice conclusion, and you can find that conclusion in textbooks. That's the standard theorem in textbooks, but what we have done is just generalize it to arbitrary vector spaces. All we needed to do was generalize the notion of an eigenvalue to an eigen polynomial. That's all. That was the inspiration for defining that. And before we finish, I just want to say one more thing. So again, fix an endomorphism T on V and Px be an eigen polynomial of T. Then the saturation exponent is at most the algebraic multiplicity. We will strengthen this later somewhere in some future lecture, but as of now, we can see this. Why is that? Again, by definition, we have this. And note this containment. Why are these strict containments? Well, because as we showed, psi pt, meaning the saturation exponent, is the largest power of px dividing the minimal polynomial of t. So all these containments have to be strict, because if at some point equality happens, equality will happen at all the subsequent points, and hence again you can reduce the degree of the minimal polynomial by using the primary decomposition theorem. So all these are strict, and hence the dimension of this guy has to be at least that much. Because this has dimension at least 1, then this has dimension at least 2, and so on. This has dimension at least the saturation exponent, because there are saturation exponent many terms here. So we can write that this is at least the saturation exponent, and therefore the algebraic multiplicity is at least the saturation exponent. Okay, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.